we will deal with later on is something called, radiation due to relativistic particles. Okay, so that like synchrotron radiation is an example for that. So we are sort of building up the machinery towards going there. So that's why, and these are relativistically moving charges that are emitting synchrotron radiation, and this is one of the most important processes in high energy astrophysics. So, and since these are relativistic particles, we have to understand relativity because otherwise we'll not be able to understand these processes. Okay, so we will actually slowly get started with that, and this is chapter 4 in the book, and I'm assuming that you have done basics of relativity already. If not, please brush it up. Okay, so I mean, relativity, mathematically relativity is not that hard. The concepts are very beautiful and subtle. Okay, so that's why these concepts escaped people like Newton and Maxwell themselves. So the maths is, once you sort of know the physical meaning of it, the maths is straightforward. So it's good to know both the maths. Oops. Just a sec. Why am I not able to edit it? Just a second. Okay. Okay, here now I'm able to edit it. Okay, so let's get started. So, oops. So we are doing a little bit of special relativity, right? So this is right. So at the end of 19th century, there was a big problem because apparently the electromagnetism of Maxwell was not consistent with mechanics of Newton. Okay, so people, for example, things like ether, right? People, so so when we talk of waves, for example, sound waves in a medium or water waves in water, these waves are moving with some speed with respect to the medium. Okay, so if you're looking at it in some other frame, these appear to have a different speed. Okay, but this was not the case for light. Okay, and lights, all observations of light, for example, the Michelson-Morley experiment and other experiments, for example, a speed of light in a moving liquid, were found to be independent of the frame that you were looking at it from. So there was a big conceptual crisis in understanding the fact that speed of light was the same irrespective of the medium in which you're looking at. This is totally different from everything else we had known. Okay, so basically, special, there are two postulates of special relativity. The first is, of course, laws of nature, right, are the same in frames moving with respect to each other with a constant velocity, right? So this is the principle of relativity, and this is known. Even Galileo's, right? So even Galileo appreciated this fact, and there are these Galilean transformations, right, which say that if you go from one frame to other, and if you just if these frames are differing just by a constant velocity, the laws of motion have the same form, right? So these are Galilean transformations. For example, if you go to x prime, which is equal to x minus vt, and t prime equals t, y prime equals y, z prime equals z, right? These are the famous Galilean transformations. So if you have a reference frame S, right, and these x, y, z, and t are coordinates measured in S, and then you have a second reference frame which is moving with respect to S with a velocity v, say in the x direction, right? So this is S prime. As long as you do these transformations, for example, your Newton's laws and so on will all be valid. Okay, so this is Galilean transformation, but it looks like these transformations are not valid when particles start approaching speed of light. So this is the first, this concept is extremely fundamental, and it is known since a long time, right? The second concept is what was the subtle one, that speed. Oops, did I start recording? I think so. Yes.
Yes, sir.
Yes, sir.
Okay. Right. So the second fundamental concept of special relativity is speed of light, c, is the same in all inertial frames. Right. So these frames which are moving with respect to each other at a constant velocity are called inertial frames. Right. So this is the fundamental concept behind special relativity. So let's say, let's consider a light ray which is emitted at x equal to 0, right? So x, and this is x prime, which is measured, and this is t prime. So these are the primed things are measured by this frame which is moving with respect to the lab frame. This is t and x, right? So this second part, what it suggests is if we imagine that at t equal to 0, the two coordinate systems sort of coincided, and we launched a light wave. Okay, so the distance traveled by the light wave, so x square plus y square plus z square, right? This is the distance traveled by the light wave, is equal to c squared t squared, right? If t is the time measured in the frame S, the fact that the distance x, y, z traveled by light, this is the total distance traveled, square of that should be equal to this. Okay, but what relativity tells us is that, and not only this is true, but also x prime squared plus y prime squared plus z prime squared is equal to c squared t prime squared, right? Not only is the speed of light the same number in this frame, it is also the same in this frame. This is not true for other waves. For example, if you have sound waves, yeah, if the observer is moving relative to the source of the sound waves, the speed measured by the observer will be different in different frames. This is not true for light, and this is what causes all this conceptual issues, right? So in order to satisfy this, right, these Galilean transformations do not satisfy this with a constant speed of light c. What we need is, so this enforces upon us, these two principles enforces upon us the fact that this innocuous looking thing, right, obvious looking thing, that the time measured by a person in a moving frame and the time measured by the lab frame are the same. This is actually, this cannot, if we assume this, we cannot satisfy these two equations. So all this sort of contradictions gave rise to these transformations which are called Lorentz transformations, right? It's actually very, very fascinating even to read the history of relativity, because a lot of this maths was actually figured out independent of independent of these first principles. A lot of this mathematics was already known before Einstein, for example, by Lorentz and Poincaré, but they did not put it all together in a form which said that, which sort of highlighted this the first point here, that the laws of physics and laws of nature are the same in all frames which are moving with respect to each other at a constant velocity, right? So these Lorentz transformations, let me write. So I'm actually assuming that you know all this, right? Is there anyone in the class who has never heard of Lorentz transformations? No, good. Yeah, that's what I hope, because this is really not a class to do relativity. This is application of relativity to astrophysical radiative processes. Okay, so so let me just write down the transformation. So dx prime is oops, what is happening? Dx prime equals, oops. What? Oh, why am I having this problem? Just a sec. Dx prime. Oh, I don't know, somehow the pad is behaving a little weird. Just a sec, give me a sec. Okay, so let me even write it in red. Let's see. Dx prime equals, so this is dx prime. So this is the coordinate measured in the x prime frame. Dx prime equals gamma dx minus v dt. Okay, so this x prime is the coordinate of some event, right? So there are events in relativity, all right, and these events are sort of denoted by x and t, right? So this is the same event. It has a coordinate x and t in frame S, and it has a coordinate x prime and t prime in frame S prime. Okay, it's the same thing. It's the same event, but it has different coordinates. Just like when we do vectors, right? The same vector will have different components in different coordinate system, but it's the same vector. In the same way, event is the same, but the coordinates are different. So this is the first transformation. Here V is with respect to V is assumed to be in the x direction, or x direction is chosen to be along this velocity V between the two frames. So this is x prime. So dy prime equals dy, dz prime equals dz, and dt prime equals gamma dt minus v dx by c squared. Right, so these are called Lorentz transformations, and so let's see. And these are, I mean, these are actually not required. I mean, because these are linear in x and t. So you don't really need a differential here, but this is how you generally write it. So these are the Galilean ones. So dx prime equals dx minus v dt, dt prime equals dt, dy prime equals dy, and dz prime equals dz. Yeah, you see, I mean, this is one difference. There is no gamma factor, and more fundamentally, this difference, what it means is that simultaneity is not frame invariant, right? What it means is that if some event happens simultaneously in one frame, that is dt prime is equal to 0, dt is not 0, right? Whereas in the Galilean universe, if something happens simultaneously in one frame, it will happen simultaneously in the other frame, in the other inertial frame. Because we are just talking about inertial frames, right? And this is a very, very different physical principle compared to Galilean invariance. Okay. So, right. I know this one looks like Galilean transformation. So, let me tell you what gamma is. Gamma is equal to 1 over 1 minus beta square root of that. Okay, this is called relativistic gamma, and beta is equal to V by C. Right, beta is just the velocity or the speed of the relative speed between the frames divided by C. This is gamma, this is beta, and right, and you see that this reduces to that when V is much less than C. Right, if V is much less than C, this is right. So, and let's see. So when V is much less than C, gamma goes to 1, and so this is dx prime is dx minus v dt, which is nothing but that. When V is much less than C, gamma is 1, and this term is actually small because V is small. So dt prime equals dt. So that's why, only when V is close to C do you appreciate this difference. And that's why it was with light that people were having problems in the late 19th century, right? There were no particle accelerators and so on at that time. The only thing that moved close to the speed of light was the light itself. So people were trying to look at relative motion of the earth with respect to the ether and so on, and all those efforts failed because there is no ether. There is no medium. I mean, speed, light travels the same way in all frames. Basically, this is this principle. Okay, so there is no ether, which people were trying to look for a medium in which light is at rest, in which light travels at sea, and other media light will travel at different speeds. Okay, so these are Lorentz transformations. You have to know this very, very well, huh? Because Lorentz transformation will be used again and again. Okay, good. So there are consequences of this. You must have heard of things called Lorentz contraction. So actually, I want someone to tell me about Lorentz contraction rather than me telling. So if someone wants to unmute himself or herself and tell me about Lorentz contraction, I'll be very happy. Anyone?
I mean, it's like that.
First, tell your name.
Yeah, sir, I'm Kinjal Roy.
Okay.
So say I am in a frame, and I see a say a scale of unit length of
Uh-huh.
1 foot, and it is moving with a velocity v. So we will see that the length of that, if I am stationary and there is a relative motion between me and the scale, I
Uh-huh.
will see it shorter.
Okay.
We
That's
will see
right.
that there is an apparent shrinking of the scale, but
Right.
in the frame of the, I mean, if I go to the frame of the scale, it will be still the actual length.
Right. And from the frame of the scale, the person, the observer,
Yeah, will be yeah.
right. So this is a consequence of uh, simultaneity not being the same, right? So when you're measuring a length of something, what are you doing? Say if you are measuring length of something in frame S, what do you do? In the frame S, you have say some scale or something, right? You want to measure this x min and x max, right? The distance between the two ends of the scale at the same time, such that, at the same time, meaning dt is equal to 0 between the measurement, this measurement and this measurement is done at the same t, right? In that frame. Uh, so let's say that frame, uh, so so dx prime is equal to gamma dx, right? If dt is equal to 0. So basically, what does it mean? In my frame S prime, in which you are moving relative to uh, frame S, where the length was measured at the same time with dt equal to 0, dx prime uh, is this, right? Uh, so Right, so when you're measuring the length in frame S prime, how do you measure it? You measure it such that dt prime is set to 0, right? And if you set dt prime to 0, then if you look at this equation, right, dt uh, dt equals v by c squared dx. If dt prime is 0 and dx prime equals gamma uh, dx minus v, dt is v by c squared dx. So this is equal to gamma dx 1 minus beta square, right? 1 minus beta square is 1 by gamma square. So this is equal to dx by gamma, right? So uh, so if you measure this in frame S prime, it will appear to be dx by gamma. That is, it's contracted. The fundamental point is when you define something's length, it has to be measured simultaneously at in that frame. Okay. So this is Lorentz contraction. So if you have a scale in its rest frame, if its length is L0, right? If an observer is moving relative to it, its length will appear to be L0 by gamma. Okay, so this is Lorentz contraction. There is also another very basic concept related to this, which is called time dilation. So what is time dilation? So does anyone want to speak up? Maybe someone apart from Kinjal.
Yeah.
Yes, who
Yes,
is it?
sir.
Who is this?
Sir, उत्तर होता.
Shipra, yeah, please go ahead. What is time
Yes.
dilation?
When we keep a clock in the moving frame of reference,
Right.
which is moving relatively to the stationary frame S. Then when we observe from the stationary frame of reference S, then it is the time will go slows
Uh-huh.
down. This is called time dilation, and we get the more time. That means we get gamma times the proper time. Gamma times
Yes.
of the proper time of
So
which we
dt
observe in the
equals
yeah.
gamma d tau. So this is the proper time.
Yeah.
Yeah. Right. So this is the time measured in clock's rest frame. Right. So if you are measuring time between two events, it will be the shortest in the rest frame of those events. Okay, whereas it will be longer. Like if you have a clock, in the rest frame of the clock you will measure the shortest time. If you're moving relative to the clock, the time between two events will be longer. This is called time dilation. So how do we understand? So do you know any experimental, I mean, how did people measure time dilation experimentally? Does any,
Satellite.
how,
Sir,
From
clock.
cosmic ray experiments
Yeah, yeah.
performed
who is
in
that
Darjeeling, I think.
spoke
This is
cosmic ray?
Aratrika.
Okay, good. How did they
Muon
use,
experiments, yeah.
how do
So
you know?
they checked the number of particles that were decaying at two different heights,
Yes, so this is the
and the expected lifetime
muon
is
decay. Yes, that's correct.
yes, sir.
So do you know the principle? What was the principle?
Mm, principle. Um, maybe not.
You can try. Do you want to try? Let's say muons have some half-life in their rest frame, right?
Yes, sir.
Okay. Now what will happen? So this is the
So
half-life in their
the
own rest
half-life will
frame.
increase in the moving frame.
Yes. So what happened was muon had a certain half-life. So what happens is you have your Earth, okay, and you have atmosphere, and these high-energy cosmic rays hit the atmosphere, and they generate these particles like muons and so on, right? If the half-life of this muon is very short, you don't expect a lot of muons to be present on the ground, okay? But because these muons are moving at very close to C, because of time dilation, the half-life measured in the lab frame, which is the Earth frame, is actually much longer than the half-life in its own rest frame. So a significant flux of muons was observed on the ground, and it was consistent uh, with this formula. Okay, so this is actually the idea. Okay, let's see, how do we understand time dilation according to Lorentz transformations? Right, so proper time means dx is equal to 0. You are measuring time at the same location, right? So the fourth equation in Lorentz transformations gives you dt prime is equal to gamma dt, right? Because dx is 0. So the time measured in a frame where positions are not the same, that is, if you're in the rest frame of the clock, the time will be longer. Is it clear? Basically, when we said dx 0, that means you are in the frame of the clock. Your location of the clock does not change. This is time dilation. Uh, and length contraction is, again, if you are measuring the two ends of the rod in the rest frame of the rod, then the length of the rod will be the longest. In any other frame, the two ends are measured at the same time in that frame. Okay, so this simultaneity the fact that simultaneity depends on the frame is very different, and it causes a lot of non-intuitive effects like this. Okay, good. So this is Lorentz contraction, time dilation. Okay, what about velocity transformation? So velocity transformations. So we want to transform velocities from one frame to other. Okay, so let me actually go back to this picture. Now we will actually deal with situation like, S and S prime. We will deal with situation in which we are in the lab. So this S frame is the lab frame and S prime is the particle rest frame, right? So we will actually, like, for example, when we do synchrotron, we will calculate things in the particle rest frame, right? For example, our Lorentz formula for power, right? Lorentz formula for power, 2/3 E squared A squared by C cube, right? The power emitted formula is calculated in the particle rest frame, right? We're assuming the particle to be at rest. It is accelerating, but its instantaneous velocity is 0. You see what I'm saying? So what we will do eventually is we will transform from this frame S prime to S, particle rest frame, to the lab frame. So and for that we will actually need a lot of velocity transformation. So let's look at velocity transformation. What we want to do is we want to go from frame S prime to S. Let's see. So let's say there is a let's see. So let U be the velocity, U prime be the velocity measured in the frame S prime. So what is U prime? So you have this frame S prime. In this frame, right, you have some particle moving or something. It has a velocity of so this is, right, so this is some velocity U prime of some particle in frame S prime. Okay, what is U prime? U prime is nothing but dx prime by dt prime. If x prime is the coordinate of the particle in frame S prime, if x prime is the coordinate in front, this is the definition of velocity measured in frame S prime. Okay, so we are given U prime and we want to get U in the lab frame. So this is your lab frame S, and this is moving with velocity v in the x direction. So distinguish between v and u, right? U is the velocity of some particle measured, U prime is the velocity of a particle or something, or measured in frame S prime. We are interested in finding the velocity of the same particle in frame S. Okay, so this is the definition of U prime, and this is the definition of U, right? This is nothing but dx by dt. Right? Rate of change of position is velocity. So let's see. Now let's look at the Lorentz transformations. Just a second. So, right. Right. So this is the transformation going from S to S prime. We are going now trying to go from S prime to S. That's fairly simple, right? We all you have to do is let's just write it. Dx equals gamma dx prime plus v dt prime, right? All you do is change v to minus v, right? And you get equations that tell you how coordinates transform from primed frame to the unprimed lab frame, right? So dy equals dy prime, dz equals dz prime, and dt equals gamma dt prime plus v dx prime by c squared, right? This is the inverse transform of this. What you have to do is change v to minus v and x to x prime. You get this, and t to t prime. So let's do it. So what do we want? We want, so what is the velocity? So u is right. So let's see. So ux in the x direction, what is it? This is nothing but dx by dt, right? This is the definition. So we just take the ratio of this and this. What do we get? We get dx prime plus v dt prime divided by dt prime plus v dx prime by c squared. Okay. So we can actually, and this is nothing but, let's just divide dx prime. So this is dx prime by dt prime. So this is ux prime plus v. So all I'm doing is just dividing it by dt prime, and I'm also dividing this by dt prime. So what do we get? We get ux prime. So dx prime by dt prime is ux prime plus v divided by 1 plus v ux by c squared. This is simple, right? So this is ux. This is how velocity is given in the unprimed frame in terms of the velocity in the primed frame and the frame velocity, the relative velocity between the frames. This is the velocity transformation law in the x direction. What about in the y and z directions? So uy, you have to just do this. Now you have to just divide dy by dt, right? So this is equal to dy by dt. This is equal to, how do you do this? Dy is dy prime, and dt is gamma dt prime plus v by c squared dx prime. What does this give you? This gives you uy prime by gamma. Again, I'm dividing by dt prime, so this is 1 plus v ux prime by c squared. Got it? This is uy prime. Similarly, z will be an analogous expression. Just replace y by z. Okay? And notice this 1 by gamma here, it's not present here. So you see, so these velocity transformation formula are very interesting, right? Suppose ux prime is equal to c. That is, you are looking at light traveling in the x direction. Sorry, is equal to c, not 0. You're looking at light traveling in the x direction, so its velocity will be c. And so let's measure ux. What is ux? This is equal to c plus v divided by 1 plus v by c. What is that? That is nothing but c, right? So this manifestly tells you that if you have light moving with the speed, so basically what this tells us is speed of light is frame independent, right? This had to be true because Lorentz transformations were constructed in order to satisfy the second principle of relativity. You see this point, right? If you put ux prime equal to c, and if I substitute in this velocity transformation formula, the velocity measured in the lab frame S, is nothing but c, which is nice, right? That and this is irrespective of v. So basically, speed of light is the same in all frames. Good. Any question? No? Okay, good. I mean, these are deep concepts, and I really, and relativity is also very beautiful and physically absolutely important. And for example, just as Newton's laws are very well established, there is no doubt about them. Relativity is very well established. Special relativity, no one doubts it. Similarly, quantum mechanics, Schrodinger's equation, no one doubts it in the regime where it is applicable. Similarly, general relativity, no one doubts it in the regime where it is applicable. So these are really cornerstones of modern physics, and that's why we have to learn all these in our curriculum, because these can be modified, but in the regime where these are valid, there is no doubt about the validity of these equations. Okay. Okay, now so this was when the velocity was along some direction. Now suppose we want to do so let's actually just write this. So u prime, let me just write what I'm writing, and then so is equal to u parallel prime plus v divided by 1 plus v u parallel prime by c square, right? Now what I'm saying is, instead of velocity v being along the x direction, there is some direction which is the relative velocity between the frames. Okay, so I take my velocity, so this is my u prime, okay, and I take the parallel component along the relative velocity and the perpendicular component in the perpendicular direction. So this is my u parallel prime in the direction of v hat prime, and this transverse direction is just u perp prime, right? This is all in the frame S prime. So I've just sort of written these things which I derived assuming v to be in the x direction. This is nothing but this equation, right? This is nothing but that. Instead of writing v, instead of writing ux prime, I'm writing u parallel prime. Similarly, u perp, u parallel, u perp is equal to, I'll use these equations. This will be u perp prime divided by gamma 1 plus v u parallel prime by c squared. Okay, and this the perp is vector, this is the magnitude. Okay. So these are the velocity transformations. Any question? This is actually very important. These velocity transformations will be used again and again further. So make sure that you understand it. Okay. Now this was going from S prime to S. What about the other way? All you have to do is go change v to v minus. So u parallel prime is equal to u parallel minus v divided by 1 minus v u parallel by c square, right? All I have done is change v to minus v and u prime to u. And similarly, u perp prime, and you can actually verify that these are correct. U perp divided by gamma 1 minus v u parallel by c square. Okay. What about the direction of velocity? Okay, so let's say in frame S prime, okay, in this frame you have this velocity this is u parallel, and you have this, this is the velocity u prime. So this is all in prime frame. This is u prime, and this is u perp prime. Okay, and this angle, let's say, call it theta prime. Okay, this is the angle. So this is the angle between the v hat direction, velocity, the frame velocity direction, and the direction of particle motion, the particle whose velocity we are interested in transforming. Right? This angle theta prime is the angle between u prime and v. This v is the relative velocity between the frames s and s prime. Okay, so let's see, what is tan theta prime? Or what is, similarly in frame S, right? You can actually define an angle theta, which is u perp, u parallel, and u. Right? And this is angle theta. This is not theta prime, theta. This is in frame S. And this again is the velocity between the frames. Okay, so what is tan theta? Tan theta, right? Tan theta is equal to u perp. Now u perp, I use u perp. When I don't put a vector, it is the magnitude of u perp. Okay, and when I put a vector, I am sort of implying the vector sign. So this is actually, this is actually vector because I am sort of drawing the direction. But this is what is tan theta? Tan theta is nothing but u perp divided by u parallel. Right? Now the question is, how is theta related to theta prime? Right? So basically the question is, if you have some particle which is moving in your s prime frame along certain direction, in which direction does it appear to be moving in frame s? That's the question. Okay, and this is called aberration formula. How do the angles transform? Angles related to these velocities measured in frames s and s prime. Aberration formula. Okay. Oops. Just a sec. Let's see. So this is tan theta. So all we have to do is just substitute for. So tan theta is equal to u perp by u parallel. So this is u perp and this is u parallel. So this is equal to u perp prime divided by gamma. This is actually equal to u perp by u parallel, right? In the S frame, 1 plus b u parallel prime by c squared divided by u u parallel prime plus b, and in the numerator we have the same formula, same factor, 1 plus b u parallel prime by c squared. Okay, so this just goes away. So this is your tan. So tan theta, the angle theta measured between the velocity of the particle and the frame relative velocity in frame S is equal to, so let me do this, u perp prime by u parallel prime divided by gamma 1 plus v divided by u parallel prime, right? This is what I get, and u perp prime by u parallel prime is what? Tan theta prime divided by gamma 1 plus So yeah, 1 plus v by u parallel prime. So this is nothing but v by u prime u prime cos theta prime. Right, or this is nothing but u prime sine theta prime divided by gamma u prime cos theta prime plus v. This is how your angle theta measured in frame S relates to angle theta prime measured in frame S prime. So this is how theta changes. What about the azimuthal angle? The azimuthal angle phi equals phi prime, right? So this angle theta is in the plane of velocity u prime and v, and azimuthal angle measures, the angle in the transverse direction, and because there is no motion in the transverse direction, the angle remains the same. Okay. Okay, so this is actually the aberration formula. Tan theta is equal to this. This is how theta and theta prime are related. Now when when we are actually we are dealing with these u primes, what we will actually be interested in later is that we will actually look at photons being emitted. We will look at photons being emitted in the particle rest frame. So we will be looking at photons in frame S prime. Photons basically emitted, right? For example, if you have dipole radiation in the particle, this is like particle frame, right? So this S prime frame, we'll use it again and again. This is the particle rest frame. Frame S is the lab frame. Okay, so for photons, what happens? For photons, u prime is equal to c. Right? Photons are moving at c, speed of light. So what happens in that case? Tan theta is equal to sine theta prime divided by gamma. V is not c, V is V, but u prime. We are actually looking at photons emitted in S prime frame. So u prime is c. So gamma cos theta prime plus v by c. Okay. Now it's via simple trigonometry, what you can write this as the following: cos theta is equal to cos theta prime plus v by c divided by 1 plus v by c cos theta prime. So from here to here, all you have to do is sec square theta equals 1 plus tan square theta, and if you do a square root and combine cos square and sine square, you will get this. Okay, and this is aberration of light, of course, because we are aberration of light, or relativistic aberration. So what does it mean? So let's consider a situation in the particle rest frame, right? Suppose you have a particle in a particle rest frame. The particle is emitting isotropically in its rest frame. So isotropically, like for example, dipole radiation is not perfectly isotropic, right? It is something like it has this anisotropy, but it is at least forward backward symmetric. Okay, now let's consider isotropic radiation, and let's look at, so there are these rays, there is power going in all directions, and there's equal power in all directions because this is isotropic radiation. Now let's look at theta. Let's look at the photons which are emitted at theta equals to pi by 2, or theta prime, sorry, we are looking at the particle rest frame. So what is theta when theta prime is pi by 2? That's the question, right? So that's given by this equation. When theta prime is pi by 2, what happens? Cos theta equals, so the cos theta prime is cos pi by 2. So this is equal to V by C divided by 1. So this is cos theta. Or we can also write tan theta, the first equation, tan theta is equal to sine pi by 2, which is 1 divided by gamma V by C. So tan theta is equal to C by gamma V. Okay, and so let's consider. So this is how the photon, which is going in this 90 degrees direction in the particle rest frame, in frame S, this will go in some angle. So this is along V hat, of course. This is along V, not V hat. Sorry. So this is this angle theta. Right, these photons which are emitted at theta prime equals pi by 2 in the particle rest frame will be emitted at an angle theta in the lab frame, which is given by this. Okay, now let's assume that V is almost approaching C. That is, these are relativistic particles, right? These particles which are moving and isotropically emitting in their own rest frame are traveling close to the speed of light. So V goes to C, close to C, and gamma is much bigger than 1. Okay, what happens in that case? So tan theta is, tan theta in that case is of order theta, which goes like 1 by gamma, because V is almost C, and what it means is very, very profound. What it means is that all these radiation, which was sort of going isotropically, so this ray at 90 degrees has become this ray, which is at an angle 1 by gamma, right? Small angle. So most of the light, it was so emission pattern in frame S prime was a circle. In this frame, the emission pattern would be like this, right? And this, you recall we were talking about these emission patterns. So most of this light, right, this angle theta is of order 1 by gamma. So this is called forward beaming. This is called forward beaming of radiation from particles, for relativistic particles. So even if in their own frame they are emitting isotropically, in the lab frame most of the radiation comes in the forward direction. Okay, so this this concept will be very, very important, that theta goes like 1 over gamma. So if you have a relativistically moving particle, right, and if it is radiating, most of its light will come in the forward direction in an angle of order 1 by gamma. Very important concept. This is called beaming effect. Relativistic beaming effect. Right, you see, has anyone out of you looked at this Event Horizon Telescope black hole images? Hello?
The initial one, yes, sir.
Yes. Right. So you see that some portions of it are brighter than the other. One of the effect, main effect that's responsible for it is this relativistic beaming, because that material is going close to C, right? So you say, there's an accretion risk, and if you're looking from here, right, this material, these electrons which are moving towards you, a lot of this radiation gets forward beamed, right? And when you're moving away from you, a lot of this radiation gets back, beamed in the opposite direction. So this will appear brighter and this will appear dimmer because of this forward beaming, the relativistic aberration. Okay, this is also true about jets. If you look at radio jets, sometimes from these radio jets, quasars or micro quasars, you only see one side. Why is that? Can you make a guess why you would see only one side of a jet? It's related to this beaming effect. Because
it's only in forward direction.
Yes, only the forward direction stuff is getting relativistically beamed. So all this radiation, which otherwise would have gone isotropically, is coming towards the observer. So this gets boosted, and the other guy, where you are in the opposite direction, this gets deep, this gets dim. So that's why you only see one-sided jets. Okay, so all these obscure and mathematically and conceptually difficult things have very real observational consequences. Okay, and this is very, very important. This is called beaming effect or relativistic aberration. Is the idea clear? Because this will come again and again. Okay, good. If you have any question, you can ask it. Otherwise, let me move on. So let's go here. Okay, the next topic is that we are going to do is Doppler effects, relativistic Doppler effect. No, Doppler effect has been around much before relativity, right? The siren of an ambulance appears shriller when the ambulance is approaching towards us compared to when it is moving away from us. So this effect is known much before relativity, but what happens in relativity is the question. Okay, so let's actually look at this setup. Okay, so let me draw something. So let's look at first. Okay, so let's see. Right. So suppose there is some periodic motion. Let's say cyclotron motion. So there is a particle which is sort of going around in a circle, say because of magnetic fields or whatever. So so this is in so this is like the so dt is equal to gamma dt prime, right? This is just time dilation. So basically this is the time interval measured in lab frame, and this is time interval measured in rest frame of the particle. So for example, let's consider a particle. It goes around in a cyclotron orbit, comes back at this position, so at the same position, if we measure its time period, that's dt prime, or delta t prime. This is period measured in the rest frame, because it's measured at the same position. Dx prime is equal to 0. The same event, frequency of this orbit measured in the lab frame, will be this, longer. Okay, so for example, this gyro frequency or the Larmor frequency. So if you have magnetic fields into or out of the board, you have circular motion of particles, charged particles. So this so this omega is equal to omega naught by gamma. This is the so this is frequency. This was time. This is frequency. So this is in the lab frame. This is the rest frame. So the frequency in the lab frame is smaller because the time is longer. So lower frequency. So this is the rest frame. All right. Okay, so basically you have some periodic motion of an emitting particle, and this is how the time period between this periodic emitter measured in the lab and in the rest frame is given by. Okay, now let's consider this situation where this particle is actually moving with some velocity v. Okay, and you're trying to observe it. So it's emitting photons. Observer, and this particles comes at this location, and this is in the lab frame. This is in the lab frame. So this angle is angle theta. You're looking from here, so the observer is looking from this direction. Okay, so let's consider. Okay, so now let's call these times. This time t1, t2, okay, t3 and t4. Let me actually define what these times are. T1 is the time when photon emitted at position 1, at this position. Okay, t2 is the time when for example, it has sort of completed one orbit, or some orbits. This is the time there is another photon emitted. Okay, T3 is the time when this photon is measured by the observer. Just a second. So T3 is the time when the observer measures this photon which was emitted at time T1. Okay, all this is done in lab frame. Okay, good. So let's see how is it. Let me just write an equation: C times T3 minus T1, right? What is this? This is nothing but the distance traveled by the light when it sort of starts from here and it reaches the observer, right? And actually, let me also draw something. Okay, so this is light travel time from here to the observer. Now in that time, in that transit time, this particle has moved to the position 2. Okay, so how much is this velocity? Just by geometry, this is v. So this distance, right? This is v t2 minus t1, and this is v t2 minus. cos theta. This extra distance that the photon emitted earlier has to travel. So this is equal to v t2 minus t1 cos theta. So this is this part of the distance, right? So right. So this is this part of the distance and plus c t4 minus t2. Right. So this is nothing but this distance, right? This distance and this distance are equal, right? Because these are parallel lines going to the same place. So this is equal to right. So this full distance is equal to this distance plus this t4 minus t2. Okay. Now what we are interested in is what is the time between the arrival times of this photon and this photon. So basically we are interested in t4 minus t3. Right? Basically we are interested in how is t4 minus t3 related to t2 minus t1. Okay. We want to be able to write t4 minus t3, the arrival times in terms of the emission times. How do we do that? So we actually rearrange this equation. So let's see what this equation says. This is the light travel time along this line, right? So this is equal to this length, which is just this, plus this extra length. This is t2 minus t1 is also the time in which light travels from here to here and the particle travels from here to here. So let's see, let's rearrange it. C times T4 minus T3. What am I doing? I am actually bringing that in this direction. So right is equal to so T4 and T3 goes there. T2 and T1. So C times T2. Oops. T2 minus T1. So that goes in the other direction, minus V times T2 minus T1 cos theta. Okay, I just rearranged this equation where I was actually writing this distance in terms of the light emission and observation times. Okay, so this is nothing but C T2 minus T1 times 1 minus V by C cos theta. The C, this is nothing but delta T observed, and T2 minus T1 is nothing but delta T emitted. And everything here is in the lab frame. Right, so if delta T m is the time between photons emitted here and here, the time measured by an observer is given by this. So right, so you see, suppose you have an object which is traveling in this direction and you have an observer looking at the same direction. So basically theta equal to 0. What happens in that case? And suppose V is, let's say V is equal to C. The particle is moving at C and it's emitting photons. Now all these photons that are emitted along the line, right, of its travel are also traveling with the same speed as the particle. So all these photons which were emitted with an interval of delta T m will reach the observer at the same time. right? Because the particle is also traveling at the same speed, and the photon are also traveling. So delta t observed basically will be 0, and that's what this is actually showing. That all these, the interval between the photons that are observed is much shorter than the interval between the photons that are emitted. Okay, this is called light chasing light effect. Do you see why I'm calling light chasing light? This particle is actually moving at almost c, right? And it's also emitting photons as it is moving at speed c. And all these photons which are emitted here, 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 and here, right? All of them reach the observer at the same time. Okay, so that's why this is light chasing light. If particle moves at the speed of light, the light emitted by it and the particle itself will hit you at the same time. Okay, this is actually very, very important. For example, in gamma ray bursts, right, people measure like delta t of the gamma ray emission. Okay, this is actually very short, right? And one of the reasons this is very short is to do with this, that the jet of the gamma ray burst is actually, the particles in the jet are moving towards you. So there is a large light chasing light effect, which makes the observed interval between the photons much shorter than the interval in their own rest frame. Very, very important effect. Are you able to understand what I'm trying to say? Light chasing light. The other effect that we were talking about previously was aberration. That is, most of the photons come in the forward direction, in the close to the direction of the motion of these relativistic particles. This is slightly different. This is the light chasing light effect, that the interval in the observer frame is much shorter than the interval in the emitter frame. Okay, so this is that. So this is the light chasing light formula. Again, the angle theta is the angle between the velocity of the particle, and the direction of the light. Like in the language of our previous slide, right? So this v is the frame velocity, and we are actually we are taking this case u is equal to c. We are actually talking about photons now. We are measuring photons, velocities, and so on in the lab frame. And this is the boost between the two frames, between particles and the lab. Okay, so this is this, but we know that delta t emission is nothing but from this, right? In the emitter, this is again measured in the lab frame, but this is equal to delta t rest times gamma, right? The time interval between the emission of these photons, or whatever, an orbit, is equal to gamma times this, or in other words, this is equal to omega is equal to omega not by gamma. So this is in the particle rest frame, in the particle frame, the frequency in the particle rest frame. This is the frequency in the lab frame. So delta t observed is nothing but omega nothing but omega. Okay, let me actually clarify this a little bit. So what is delta t observed? Delta t observed is equal to delta t emitted 1 minus v by c cos theta. Okay, and what is delta t emitted? Say, you have some, say, gyro motion, some periodic motion, so delta t emitted. Let's say, forget about any physical motion. What you say is this source is emitting, releasing photons after every time delta Tm, right? So there is a source of photons which is moving, okay, and it is releasing photons after time delta Tm as measured in the lab frame, okay. So this is equal to delta T rest times gamma, right? Because the lab frame time interval is longer than the rest frame time interval by this factor gamma. And let's measure this frequency. Frequency as measured in the lab frame is nothing but 2 pi by delta T observed. So basically this is the setup, that you have this particle moving, it emits photons and after every interval delta Tm as measured in lab frame. Question is what is the frequency of photons measured in the lab frame by an observer? Okay, so this is this is equal to, so if I substitute for this from here, this is equal to 2 pi by delta T m 1 minus v by c cos theta. Okay, and we know that delta Tm is 2 pi by delta Tm, right? 2 pi by delta Tm is nothing but delta T rest times gamma, right? Delta Tm is nothing but delta T rest. So that's the time interval in the rest frame, and this is because of this Lorentz. This is because of time dilation. So what do we have? 2 pi by delta T rest. So omega is equal to 2 pi divided by delta T rest is omega prime. Right? This is the frequency. This is the frequency between the photons emitted. Right? This is nothing but right. So omega prime equals 2 pi by delta T rest. This is equal to 2 pi by delta T m divided by gamma. So what we have is omega equals omega prime divided by 1 minus v by c cos theta times gamma. Right, so this is nothing but omega prime equals gamma omega 1 minus v by c cos theta. This looks very similar to our Lorentz transformation, right? There's a gamma here and there's 1 minus v by c. This is the Doppler formula for frequency. This is the frequency in the lab frame of the in the rest frame of the particle frame. This is the frequency measured in the lab frame, right? And this theta is the angle in the lab frame between between the particle and the direction of the light. So, I mean, this actually can be seen by 4 vectors too. We know that omega and k is a 4 vector. We'll actually come to this concept later, but this is like a physical way of seeing Doppler formula. Right, so this is how omega prime goes, like can be written in terms of omega, and of course we know the inverse transformations are gamma omega prime 1 plus v by c cos theta prime, right? This is always true, and this actually you can check that there is this relation between theta prime and theta, this aberration, right? This aberration formula. You can actually check that this is consistent with that. So this is from lab to particle. This is from particle to lab. This is Doppler formula. This is relativistic Doppler formula. Right? And you see, in normal Doppler formula, we have to know the speed of observer and emitter relative to the speed of the medium, right, in which the wave is traveling. Here only relative velocity matters between the observer and emitter. So this is relativistically only v observer minus v emitter matters. There's no medium, because there's no ether. The whole thing does not apply to light. So this is the difference between from classical Doppler formula. Okay, so last thing is I want to just define proper time. Proper time. Proper time is the time measured in rest frame, right? So there is something called right. So c squared d tau squared is equal to c squared dt squared minus dx squared plus dy squared plus dz squared. Okay, so this is a quantity which is called interval, right? So this is a Lorentz invariant. So this is an invariant, right? So this is basically the, for example, we have distance between particles in distance space. So this is like a distance between events in space-time, right? So just as the Euclidean distance is an invariant under transformations, this is the invariant, and you can actually see if you put dx, dy, dz 0, then d tau is equal to dt. Basically, this is called the proper time, right? This is the time measured in the rest frame of the particle where dx, dy, dz are 0, right? Things are measured at the same place, and d tau is a Lorentz invariant. It's the same whatever frame you are measuring in, because this corresponds to this interval. And we know that so if you are in a frame in which particle is at rest, this is S prime frame and this is S frame. So d tau is the time measured in this S prime frame where particle is at rest, and there is a relative velocity v between them. So so dx square plus dy square plus dz square is nothing but v squared dt squared, right? So d tau squared is equal to dt squared 1 minus v squared by c squared. Right? This is nothing but d tau equals dt by gamma. Right? This is nothing but Lorentz. This is nothing but time dilation. The time measured in the particle rest frame, when you are measuring time at the same location in space, the time is the shortest. Otherwise, time is longer. So this is proper time. Okay. And this is how it is related to the time delta t measured in some other frame, which is moving with respect to velocity v with respect to the rest frame. Okay, so this is about like the basics of relativity that we are going to use. In the next class, we'll actually, this is more like a intuitive introduction to relativity. The more formal stuff is like 4 vectors and matrix. You can actually learn all this in matrix form, transformations, and so on. But we are actually not going to go in great detail of all this. We are going to use relativity as we need it for treating radiative processes in astrophysics. Okay, so I encourage you to brush up your concepts in relativity and to read the book. Start reading the book. Try to understand these concepts. These concepts are extremely subtle. Math is not that hard. It's the concepts which are. So, try to go through the material that I covered today. Okay? Okay, then let me stop sharing. Any question, by the way? Oops. Any question? No? So I will stop presenting and I will turn off recording.